In this video, we'll discuss the derivative shortcut for exponential functions. Recall that exponential functions are in general written as some base raised to the power. So the power is the input of the function. And of course, a very special exponential is the exponential with base e. So now we have the derivative shortcut rule for exponential functions base e. There it is, right? It's a very interesting function because, think about it, it's a function whose derivative is itself. So this is very, very useful in mathematics. And what I'd like to do is take this fact and let's extend this a little bit further using the chain rule. So this only works if you have just e to the x, but that's only one single function. We certainly know that we can extend this even further. So let's do that. So in particular, think about it this way. E to the x, well, the base is e, and the input is x, right? If I write this as f of x, function notation. So that means another way to write this would be something like exp of x, right? This is just another way of expressing the fact that x is really the input of this function, okay? So that means that I can extend this a little further by saying, well, what if I don't have x, but I have a function of x? Okay, so think of it as a composition of functions. That is, what if I define g of x as e to the f of x? That is, it's e raised to some function of x. Now, we can use chain rule in order to differentiate this and the knowledge of this up here. And that came from the definition of derivative. We proved this using the definition. Okay? So let me show you. The way that this is going to work, the derivative of g of x now, using the chain rule, is as follows. So if I differentiate g with respect to x, remember with chain rule, what we do is we differentiate the outside function and then differentiate the inside function. Right? We sort of do this as an onion peel. So the outside function here is e to the something. This is outside. And the inside is f of x. Okay? Notice that that's how I've written this, right? Here's the outside, here's the inside. Here's the outside, here's the inside, right? And I could write little parentheses if I wish for the inside part. So that means the derivative here is going to be, well, I have to differentiate the outside. The derivative of the outside is just e to the whatever again. So e to the f of x, that's the derivative of the outside. And the derivative of the inside is going to be, well, f prime, right? Whatever f is. Okay? So again, this part is the derivative of the inside. And this is obviously the derivative of the outside. Okay, that's the chain rule. And again, the thing that makes this complicated is it's not so easy always to recognize that the outside function is e to the x, or e to the something, and the inside function is whatever that thing is. In this case, I called it f. Let me do a short example to show you how this works. In order to come up with a derivative rule for all exponential functions, let's start with looking at the very special exponential function, and that's the exponential with base e, e to the x. And once we are able to come up with the derivative formula for this special exponential function, we can use the change of base formula from algebra to extend it to all exponential functions. So let's get started by looking at the definition of derivative, and this will hopefully convince you of exactly what the derivative of this function is. So remember that if I have f of x plus h, I just replace all x's with x plus h. So therefore, f of x plus h is e to the x plus h. And so now I can write the difference quotient in terms of these two values. This is equal to the limit as h goes to 0. And the difference quotient is going to be, well, f of x plus h is e to the x plus h minus f of x, which is e to the x. And now I'm going to use the property of exponentials, which is that the same base with the same base and a sum of powers, that can be rewritten as a product of two bases with these powers. So I can rewrite this as the limit as h goes to 0. There's still an h down here. This sum here can be written as e to the x, e to the h, minus e to the x. Okay? This is due to the properties of exponentials. And now, notice that I have an e to the x that's common in both parts of the numerator, which means that I can factor that out of the numerator. Secondly, notice that if I'm taking a limit on h, then x's are actually constants because they're not changing at all with respect to h. So once I factor out e to the x, I can actually pull it outside of a limit. So let's go ahead and do that. That is, I can write limit as h goes to 0. There's an h down here. I factored out the e to the x. What I have left is an e to the h minus 1, right? Just factored that value out of this numerator. And again, as I was saying, this has no h in it. So because it has no h, I can factor it out of the limit. It's not affected by how h changes. So if I pull that outside of the limit, this is e to the x that comes out here, what I'm left with is this limit with exponentials in it, okay? And if you put these values into some kind of calculator and you compute numerically what happens when h gets very small for this particular quotient, what you'll find is that when h shrinks towards 0, this entire quotient heads off toward 1. Okay? And you can do that numerically. So if you can convince yourself that this limit actually goes off to 1, then in fact, since this is the definition of derivative, I've computed the derivative of the exponential with base e. That is, the derivative is in fact itself back out again. Okay? Okay, so here's an example. That is, y is defined as e to the x squared plus 1. Here's my function. Okay? Notice that I've written my generic rule up here. And all I've got to do is identify the inside part and the outside part. Well, the outside part's easy. The inside part's what we really have to identify. So in other words, what is f of x? Well, in this case, notice that this is e raised to the polynomial here, x squared plus 1. So that means that in this case, my f of x is x squared plus 1. And that means that I can differentiate this. So dy dx is going to be using my formula. I know it's the derivative of x squared plus 1, which is, of course, 2x. And I multiply that by e to the f of x. Well, f of x is x squared plus 1, so you just put the function back again. So e to the x squared plus 1. So there's the derivative with respect to x. Okay? And notice, by the way, that this rule in the green box is really just a more general case of the red box. The red box is a special case of the green box. Meaning that if f of x is x, what's the derivative of x? It's 1, right? So if f of x is x, you'd have e to the x multiplied by 1. So in fact, if f of x is x, you get the red box. So in some sense, the red box is if f of x is equal to x. Okay? But this is the shortcut rule for exponentials, and then we extend it a little bit by thinking about the chain rule. Okay? And if we think about the chain rule, then we can differentiate exponentials with anything in the exponent part of it. Okay? And we just use this definition. So this is my working definition, the green box here. This is going to be the definition that works for more general kinds of exponential functions. So what about more general exponential functions? Remember that this is just a special exponential function with base e, right? This is only one class of exponential functions. But it turns out that we can use some properties of algebra and what we know about the derivative of exponential base e to extend this shortcut rule to all exponential functions. Okay? Recall that a general exponential function looks like this. It's written as the base raised to the power, right? The input is the power that you raise the base to. In this case, we just had exponential base e, but in general, it could be any number. okay? It could be any non-negative number. But we also say that we don't want b to be 1, because if b is 1, then it's not exponential anymore. Also recall that sometimes we can write a constant in front of this as well, but without any loss of generality, we can assume that the constant is 1. So we're just going to assume the constant is 1 and come up with a derivative for the more generic exponential function base b. So let's go ahead and do that. Again, I'm using what I know about the derivative of the exponential base e and the change of base formula that we've seen in algebra. So let's go ahead and do that. In particular, one thing that I need to use before I get to that is remember that the log base e of e to the x is equal to x. That is, that logarithms and exponentials are inverses of one another. And every time we do this, provided the base is the same, then what we always get back out is the input. Notice the input in the exponential is x. That always comes back out. So that's one fact that I'm going to use. Here's what I'm going to do. I'm going to start with b to the x, and I'm going to rewrite this in terms of exponential base e because I know something about that. So if I rewrite this, this becomes equal to, notice this is e to the natural log of b raised to the x. Why does that work? Well, think about it. Remember that I said log of e to the x is x, right? In this case, exactly the same thing's happening. Notice that what we get here is this is my input now. So e to the log of something is just that something. So in some sense, the stuff in the parentheses here is equivalent to just b. That's why I can write b to the x as this thing to the x. And of course, we know from properties of exponentials that if I raise some exponential to a power, it's the same thing as multiplying the corresponding powers. So that means that I could rewrite this as, this is just equal to e to the x log b, okay? The natural log b. All right, now I have my expression here, and what I'm going to do is now use the chain rule and what I know about derivatives of exponentials to get the derivative of the general exponential function b to the x. Okay. So, first of all, let's think about this for a second. So, remember that in some sense we want to use the chain rule here. Notice I'm going to use the stuff that's written in the green box. That is that, well look, what do I have here? I have e to the function of x, right? In some sense that's a function of x, that's not just x itself. So if I identify that as my f of x, the f of x here, according to this little box here, in this case is going to be x log b, right? Now, using my formula here, I know that the derivative of this exponential is written as f prime e to the f of x. Well, let's just write what f prime is. F prime is definitely just, well, log b is just a number, right? And the derivative of 1 is 1. Well, I should say the derivative of x is 1, right? So that means that I get log b here. Right, that's the derivative. Now what I want to do is I want to differentiate both sides of this equation. So, let me write that down. So I'm going to differentiate with respect to x both sides of this equation. Whatever I do to one side of the equation, I must do to the other. If I differentiate both sides, the equation remains valid. So I'm going to go ahead and do this. What I get here is, of course, I still have derivative with respect to x of b to the x. But that's going to be equal to the derivative of this guy. Remember, again, I'm going to use this property up here in the green box. I've already figured out what f is and what my f prime is. So all I've got to do is sort of act like all the king's horses and all the king's men and put it back together again, right? So that means that the derivative of this is going to be, well, f prime, which is given right here, it's going to be log b, multiplied by e to the f again. Well, this is just e to the f of x, right? So this is e to the x log b. Great. Okay, and so now I can sort of rewrite this a little bit, okay? Because I don't really want exponentials back in there, but I needed to use them in order to come up with the actual derivative formula for this general exponential function. So now what I'm going to do is I'm going to say, well, I can rewrite this again. I'm going to say, well, this is log b, clearly still there. This I can rewrite again as e to the log b to the x power, right? But really, think about it, this is still b. just as we constructed it. So when all the smoke finally clears, what I've got here is that d dx of b to the x is really equal to log b multiplied by b to the x. Okay? And notice that this is just equal to what's over here, and I just rewrote that down here. So now, in particular, this is my rule, my shortcut rule, for differentiating exponentials with any base b. So now I've written both rules down in green boxes here. We got the second one really by knowing the derivative of exponential base e. And now let's do an example, right? What if we have an exponential base something other than e? How about 5? So here's g of x is equal to 5 to the x. Let's differentiate g. So according to my rule, the derivative with respect to x of g of x is equal to, well, it's going to be log of my base. My base is 5, so it's log 5, natural log 5, multiplied by 5 to the x back over again. So there's your derivative. G prime of x is log 5 times 5 to the x. Okay, and log 5 is, of course, some number that we can compute. But there is the derivative of 5 to the x.